To start off, when we start using the oscilloscope here in a few minutes, what you're going to see is that every oscilloscope has a front panel like this. And on the X plane here, this really represents time. We're on the X-axis here. It's really the Cartesian coordinate system, no different than working with algebra or any mathematics. So the X coordinate here represents time. The Y coordinate here is going to represent amplitude. Okay, and you guys will see here in a second how we actually take a voltage measurement with respect to time, and that's amplitude with respect to time. And then these gradicules represent different quantities depending on what position your various controls are in. So in this case, you might call this first one here 1, 2, 3, and 4 gradicules if we call this middle a 0. Okay? And then each little tick mark here would be 0.2, 0.4, 0.6, 0.8, or 1/5 of our quantity there. Okay? So let's go ahead and take a look at a trace here. And again, in a minute, we'll actually walk over to the oscilloscope here, and we'll actually do it in real time. But first, I want to show you, if you were looking at this trace on an oscilloscope right now, we'd be able to take a measurement using this trace. The first thing we'd have to do is note what our controls are, what our control settings are. So I'm going to write controls here. And let's say that our volts per division knob was set at 5, and our time per division knob was set at 1 millisecond. And that's also the same as saying 0.001 seconds. That'd be the same thing. Let's say for right now our times 10 probe, we haven't even talked about that yet, but let's say our times 10 probe is off, and let's say our coupling is set to DC. So what that means is right now we're going to read a DC waveform using the oscilloscope screen. And this would be the trace that would show up on my oscilloscope. So all I need to do to actually take this measurement is count the number of divisions. So in this case, if I count up from my 0, this being my 0, and I count up 1, 2, 3 divisions I have, I can determine what this voltage is. So I see that my thick solid line is tracing across that third division here. Okay. Next thing I notice is that my volts per division is set at 5. So I have 5 volts per division. I have 1, 2, 3 divisions equals 15 volts DC. And how do we know it's DC voltage? We know it's DC voltage because it's a flat line. If this was an AC or alternating current, we would actually see some sort of sine wave or some sort of alternation. And we'll go over one of those here in a minute. So our voltage is 15 volts DC. We also know that that voltage is positive because the voltage in this case is above the 0 mark, this being the 0 mark. If that voltage was at 3 divisions below the 0 mark, we would know it would be a negative 15 volts DC. So in this case, it's a positive 15 volts DC. Now, when we talk about period and frequency, these really are specific to AC voltages. So in this particular case, both of these are not applicable. So we have no AC voltage. We do not have any change over time. There is no variation in this voltage whatsoever. All right, we erase these ones, and we'll move on to the next one. And again, we have amplitude and we have time. And these will be our control settings. For this particular example, our volts per division is going to be set at 2 volts. Time per division is going to be set at 2 milliseconds. And times 10 probe is going to be off. Our coupling is going to be set to AC. We know that this is an alternating waveform. We know this is an alternating waveform because it's going up and it's going down. So we do have a full alternating cycle here. So we'll go ahead and do some calculations based upon this one. Our volts per division, and when you look at voltage of an AC waveform, and the oscilloscope is one of the few meters that you can actually do this on. Digital multimeter will read AC in RMS units. Analog meter, we can read AC in RMS units. The oscilloscope is actually going to be the only meter where we can actually read a true peak-to-peak waveform. So that's kind of a unique aspect of the oscilloscope. The other thing is that the oscilloscope is really good for reading high-frequency signals. Fluke digital multimeter will do pretty well, but as soon as you get over a couple thousand hertz or 2K hertz, it starts to not keep up and processes quickly. Our oscilloscopes in the lab are all rated up to, some of them are at 10 megahertz and some of them are at 100 megahertz. So we can read a very, very quick signal, or a high-speed signal. So in this case, the volts per division, we're actually going to look at our peak-to-peak waveform. That's what we're concerned with here. We want to know what our peak-to-peak waveform is. So we pick a peak right there. That's the lower peak. That's as low as this voltage goes. Again, this would be my 0 volt level. And then we'll pick an upper peak. And that's as high as my voltage would go. And I'm going to look at the difference between the two. So if this is really 1, 2, 3 down and 3 up, I like to actually just count the full peak to peak though. So if I call this 0, if I just pretend this is 0, this would be 1 division, 2 divisions, 3, 4, 5. I can see I have 6 full divisions on my trace here. So I'm going to take my 6 divisions, and again, it's no different than it was for DC. I'm going to multiply that by my volts per division, which is 2 volts, and that's going to give me 12 volts peak to peak. I notice that my times 10 probe is off, so I don't have to do any multiplication or anything. But now I want to figure out my period. Okay? What your period is the length of time it takes for one complete cycle. And a complete cycle is where the waveform is going to repeat itself. And this is an excellent example of what we will want our trace to look like. We want as close to one complete cycle as we can get to have the best possible resolution. So I can see my waveform starts right here, and my waveform is going to end right here. And it would repeat another one if it kept going on in time. But we can see this takes up one full screen for a time period. This is going to be my period. From where it starts to where it finishes and starts over again. So in this case, I have 1, I'll just kind of count these for you. There's 1, 2, 3, 4, 5, 6. And as you get used to these, you can just kind of do it on the fly. There's 10 full divisions, okay? So it's 10 divisions. I'm going to multiply that by my time per division, because period is really a measurement of time, because we're looking at that x-axis, which is a measurement of time. So I'm going to look at my time per division, which is 2 milliseconds. So 10 divisions times 2 milliseconds, and my period is going to be 20 milliseconds. Pretty easy to deal with there. And as you get into basic electricity, the other thing you'll discover is that frequency and period also have a reciprocal relationship, such that frequency is actually equal to 1 over the period. So that's kind of a nice thing to know. And what frequency is, where period is the time it takes for one cycle, frequency is the number of cycles we get every single second. The number of these complete waveforms we're going to have in a second, okay? So what we do is we do a reciprocal of 20 milliseconds. Type that into my calculator. And I find out that this is actually 50 hertz. Frequency is always measured in hertz, okay? So that's one example there. And I'm going to put my coupling on AC. And again, we know it's an AC voltage because we have an alternation here. I do want to kind of make a note here, though. My times 10 probe is on. What that means is when we get into the lab here, you'll see that the probe actually has a times 1 times 10 attenuator. So we can actually bring this into the screen. It's kind of like attenuating that signal by 1/10. So you're only looking at 1/10 of the signal at a given time. So if you had a signal that was way too big to fit on the screen, you could turn the times 10 probe on and it would shrink and fit onto the screen. But we have to account for that. If we don't account for that times 10 probe, we're actually going to be off in our calculation by a factor of 10. So that's not going to be a good thing. So again, we'll go ahead and work through this. Our volts per division. Now the times 10 probe only affects amplitude. It only affects voltage. It's not going to affect our period or frequency. There are some scopes that will have a magnify or a gain, and those may affect both the y-axis, the amplitude, and the time axis on the x-axis. So there are some scopes that will have magnifying gain along with the times 10 probe, but every scope has a times 10 probe. It's a function of the probe, not necessarily a function of the scope. So in this case, we want to calculate voltage. So it's 5 volts per division. Well, first we've got to figure out the divisions. Let's figure out the divisions. This one's a little bit trickier. I can see I have one full division up from my 0, and then I have a couple pieces, 0.2 and 0.4. So I could take 1.4, multiply it by 2, or you could even on the scope, you could actually move this down a little bit and just look at it from a particular line and count up with the portions. In this case, I'll count up how many there are. It's 1.4 divisions up, which in this case, because it's centered on the 0, it's also 1.4 divisions down. Yep. So that's going to be a total of 2.8 divisions times 5 volts. 2.8 times 5 gives me 14 volts peak to peak. However, our times 10 probe is on, so we have to multiply that by 10. That's going to give us 140 volts peak to peak. So that's the one thing you have to take account into with the times 10 probe, is you'll have to multiply by 10 because of the probe there. Okay. The period, we'll take a look at that real quick. It's 2 divisions. You can see it starts here, ends here, and I could do that anywhere on the trace. 2 divisions times 5 milliseconds equals a 10 millisecond total. Okay, that's my period. And then my frequency is going to be 1 over the period, which is 1 over 10 milliseconds. So I'll do 10 milliseconds in my calculator and do a 1 over x. I get 100 hertz, just like that. And that's a good demonstration of what we're going to go over in lab here in a few minutes.
The sine wave being displayed is being generated from the internal arbitrary waveform generator, and is a sine wave with a frequency of 100 kilohertz and an amplitude of 900 millivolts. The signal that has then been applied to the channel A input, and the range control has been set to auto, so it automatically selects the best vertical range to give the best vertical resolution and most accuracy for any measurement. And here in fact we can see it's selected plus or minus 1 volt. So we could then use the range control to manually set the range. The menu system has been divided into 3 toolbars. So the third toolbar is for the channel setup. So here we can see the channel options for channel A, and in fact the input is a default ×1 probe, but if for example we connected a ×10 probe to the input, we could select a ×10 option, and then this would automatically scale it to ×10, so the voltage values would read correct. The second item down is resolution enhancement. So the digitizer is an 8-bit digitizer, which would give up to 256 vertical levels, but we can, by oversampling, increase the number of bits. So for example, we could select 11 bits, and we can see now we've got improved vertical resolution, so we can make more accurate measurements. Similarly, for each channel we've got scaling. So if we had a special probe, we can change the scale factors and the offsets, and there's an analog offset, and finally at the bottom there's a low pass filter. So for example, if I turn on the 1 kilohertz low pass filter, we can see it has again removed any noise on the signal, which again could improve the vertical measurement accuracy. The third icon along is the coupling. So at the moment we've got DC coupling, so we can go to AC. If we've got any DC content on the signal, that would remove that. And the third option is for high bandwidth signals to terminate into 50 ohms. So if I select that, in this case it will halve the amplitude of the signal because it's coming from a 50 ohm source. The next set of icons along are for the additional channels. So this is a 4-channel instrument, so we've got channels B, C and D available. So I'll turn on channel B and give it a range control of plus or minus 1 volt, and here we see now channel B is being displayed with its scale factors on the right hand side. In fact, we can see the signal, it's the same signal but it's been passed through a low pass filter, so it's been attenuated. So I'm going to increase the range control 100 millivolts, so now we can see it in more detail, and in fact we can see the signal has gone through the filter and been delayed in time, so we can see a delay offset in time here. Moving to the main menu bar along the top, this is a Windows pop-down menu system. So if we select File, for example, it gives a very window type pop down. Here we can open either waveforms that have been saved or any instrument setups, and similarly we can save waveforms and save setups. So for example, if two engineers use that particular instrument, they could both have their own different setup available to be loaded. And as a special option, there's a power up setting. So again, if an instrument is used in one application, it can power up in a chosen set of settings. So you can save the settings and then it will automatically power up into that front panel setup. The third item is a default reset.
The input trigger conditions can be defined in the trigger toolbar provided along the bottom of the main display panel. The first two icons are to stop and start the acquisition. So at present the data is being acquired, and if any data of interest is being displayed and captured, this can then be stopped for further analysis, and then the first icon would restart the acquisition. The remaining icons are to define the input trigger conditions. So a number of trigger modes are available. The first one is called none, and this is an untriggered condition just to monitor the data being applied to the input channel. The next selection is the auto, and this provides a stable triggered display. The next mode down is repeat mode. This is looking for a repetitive trigger and displaying the data. A single trigger mode will take one trigger and then fill one buffer, and we can force a new acquisition and acquire into just one buffer. The rapid is a special mode for acquiring as fast as possible a sequence of triggers and filling a sequence of buffers. So here we can select the number of buffers. So for example, we could choose 40 buffers and then force an acquisition into 40 buffers. So here we've acquired as fast as possible 40 buffers, and then we can step through the acquired data and monitor each buffer. The final mode is the equivalent time sampling mode. We'll return here to the auto trigger and start the acquisition again. Channels B, C or D were turned on. These could be selected as the trigger source. The following two icons are the rise and falling edge for the trigger. So at the moment it's triggering on the rising edge, and we could trigger on a falling edge. So here we're triggering on the negative edge. I'll put it back to the rising edge. This is the trigger level, so by default again it is on the 0 trigger level, and we could dial in any particular required level. So here I've selected 100 millivolts, and here we can see the trigger marker has moved up to plus 100 millivolts, and indeed we can just drag and position the trigger level, say at minus 200 millivolts with the mouse pointer. I'll return this to the center to 0, so we return the trigger level to the 0. The next icon is the memory position. So by default it's 50%, so we have 50% pre-data of the trigger point and 50% post-trigger. And again we can just use the icon and move it so I could position at any chosen point. So here we got now 10% pre-trigger and 90% post-trigger being displayed. Return it to the default position of 50%. The next icon is the position of the data relative to the trigger point. So we can select that, and then we can dial in delay time, and here we see now we had got a delay time of 3 microseconds, so the data is being displayed 3 microseconds before the trigger point. Again, I will return this to the default position. The final icon is a shortcut to the measurements menu, so here we can quickly add any desired measurement.